Okay, this video will cover the second day of our Pythagorean theorem examples here to help get you ready for the PSSA test. Starting with example 8, the problem asks us to find the perimeter and area of triangle ABC. So we have two things we need to do here, and it is asking us to round any decimal answers to the nearest 10. Well, for starters, if you take a look, we have a right triangle here with a horizontal line going from A to B and a vertical line going from B to C. So I'm going to indicate that we do have this right triangle. And the fact that we do have a right triangle and we're talking about perimeter, that should lead us to understand that we do need to use the Pythagorean theorem to find some side lengths. Well, for the horizontal side, it would have a length of 8 units, just simply counting from A to B. And from point B to C, that would have a length of 12 units. Our challenge is to find the distance from point A to C. And again, since it's a right triangle, that tells us we need to use the Pythagorean theorem. So we'll be using a squared plus b squared equals c squared, and simply substituting in the values of 8 for the one leg and 12 for the other leg, and working through the problem as shown. When you add these two sides together, you get 208, the two values together. And I guess really I should go ahead and change this to x here to be accurate for drawing. Make that little correction. But to find this with x squared, or to find what value, we need to substitute in for x to make it equal to 208. Remember, we have to take the square root of both sides. And using our calculator to find that value, x would have a value of 14.4. So, labeling the diagram here, we now have the information we need to be able to solve this problem. For the perimeter, we simply add up all three side lengths. We're doing 8 plus the 12, plus that 14.4 that we just found, for a total of 34.4 units. For the area, that formula is 1/2 times the base times the height. And if you kind of picture the triangle being turned upside down and us calling side AB the base, that would mean the base has a value or a length of 8, and the height of that triangle would be 12 units. When we multiply those values together, we get a final answer of 48 units squared. So the area is 48 square units, and the perimeter would be 34.4 units. Moving on to example 9. It says a ladder sits on the back of a fire truck. So I'll do my best to go ahead and draw this fire truck. You'll see why I'm a math teacher and not an art teacher here. And it's parked next to this building, with the window way up high. So I think I'm going to go ahead and pause this and finish drawing my diagram. Okay, I didn't totally finish drawing the diagram, so it'd make more sense for you to see how I'm labeling things here. For starters, it said that there is a 72-foot ladder, and it also said it's 26 feet from the building. Okay, and this would be forming a right angle. And it's actually saying that the the window itself is 74 feet off the ground. And we're trying to figure out if the ladder will actually reach the window. Well, what we have here is kind of a two-part problem. If you look, we essentially have a right triangle situation right here. And we're going to need to find that value of x. So since it is a right triangle situation, we are going to go ahead and do the one leg squared plus the other leg squared equals the hypotenuse squared. And I'll quickly go through these calculations. Taking the square root of both sides, x would be equal to 67.1. Now, that's right here. This is this distance from here to here. But the other thing I didn't label earlier was the fact that the ladder was 9 feet off the ground. So the distance from here all the way up to the top of the ladder is actually that 9 feet plus that 67.1 feet that we calculated right here, for a total height of 76.1 feet. So if the ladder is only if the window is only 74 feet off of the ground, and the ladder's height combined with the fact that it's 9 feet off the ground, if that reaches 76.1 feet in the air, since 76.1 is greater than 74 feet, the answer to this question is yes. The ladder sitting on the back of that truck will be able to reach that 74-foot high wind. All right, moving on to number 10. What we have here is a cylinder or a can, and they're asking us to find the radius for the bottom of the can. So for starters, what you have to understand is we have a right triangle here. And they're giving us two of the values. They're telling us that the height is equal to 12 centimeters. And this might be a new term for you here. It's the slant height. They're saying the slant height is 13 centimeters. And since they're asking us to calculate what the radius would be, they're essentially asking us to find the distance from the center of the bottom of the can all the way out to the edge. All right? And you can see that we do have a right triangle situation, so we're going to take the one leg squared plus the other leg squared is equal to the hypotenuse squared. Again, using the Pythagorean theorem. Doing some quick, easy calculations, we're able to find that the radius is equal to, the r squared is equal to 25, but once again, we have to take the square root of both of those sides to get a final answer of 5 centimeters in this case. So that's what the radius would be for this can. Now it says how many square centimeters of metal will it take to make the top and the bottom of the can? So essentially what we're doing here is we're finding this area. And to find the area of any circle, we do pi r squared. So I'm going to go ahead and put in some values here. We calculated earlier that the radius was equal to 5. So essentially we're doing pi times 25 here. When you punch that into your calculator, the area is equal to approximately 78.5 square centimeters. But what you have to keep in mind, it asks for the area or how much metal is for the top and bottom of the can. So this first calculation is just finding the area of the top of the can. Since the bottom is the exact same size, we're going to have to multiply that by 2 to get our final answer of approximately 157 square centimeters. That's the amount of metal it would take to make the top and bottom of the can. And then with letter C, if you took the entire lid off of the top of the can, what would the circumference of the lid be? Well, we have two formulas for circumference of a circle, 2 times pi times r, or pi times d, since the diameter is simply equal to 2 times the radius. Well, on this particular problem, since we calculated the radius to be 5, I'm going to go ahead and use the first formula. And that will give me a circumference of 10 pi, which I'd then substitute in 3.144, and I'd get a circumference of 31.4 centimeters. Okay, that takes care of number 10. We just have a couple more problems to go through here. Number 11 says 3 side lengths of a triangle are 7, 8, and 11. Do these form a right triangle? Well, to solve a problem like this is what you have to understand is if it is a right triangle, it means the Pythagorean theorem should work. And by work, I mean that a squared plus b squared should equal c squared. In other words, when you put the two legs in for a and b and the hypotenuse in for c, the left side of the equation should equal the right side of the equation. So let's go ahead and see. We know the hypotenuse would always be the longest side, so that means the 7 and the 8 would have to be your legs in this situation if it were to be a right triangle. So I substitute those values in. I put 11 in for the hypotenuse. And I do some calculations here. And for the left-hand side of the equation, I get 113. The right-hand side, I get 121. So I'm going to go ahead and put a slash through that equal sign because those are obviously not equal values. And what this tells me is that no, this is not a right triangle, because if it were, the left side would have to equal the right side when using the Pythagorean theorem. So we have another example down here, 16, 30, and 34. I'm going to go ahead and substitute those values into the Pythagorean theorem and see if it checks out as being a right triangle. Now you'll see in this case that the left side does equal the right, let me undo that. The left side does equal the right side, that means that this must be a right triangle, because when we put those values in for the Pythagorean theorem, the left side did in fact equal the right side. All right, and one final example down here. Some of you may recognize the number 8, 15, and 17 as a right triangle, but just because you see those values in some form doesn't mean you can automatically jump to that conclusion that it is a right triangle. So let's go ahead and see. Let's go ahead and substitute the one leg in and square. Substitute the other leg in and square, and set it equal to the hypotenuse and square that. And on the left-hand side, don't forget you'd have to add those two quantities together. Well, when you punch this in your calculator, you'll find that this is equal to 0.0064. This is equal to 2.25, and this is equal to 2.89. When I add those two terms together on the left-hand side, this is what it gives me. And turns out that no, the left side is not equal to the right side, so it would not be a right triangle, even though the 8 and the 15 and the 17 might jump out at you as something called a Pythagorean triplet, which applies to right triangles. But basically what it boils down to is the decimal's in the wrong place with that 0.08. So these are three examples where we're given side lengths of triangles, and we use the Pythagorean theorem to test to see if it is in fact a right triangle. And if you look on this last side, this is actually called the converse of the Pythagorean theorem. The Pythagorean theorem allows us to use or to find a missing side length when we know for certain that it is a right triangle. The converse is what allows us to test to see if three sides of a triangle are in fact sides of a right triangle. So I hope these examples are helpful. Thank you and have a nice day.